Yes. Good afternoon. So this will be our last class. Okay. Um, so as I said in the previous class, I will just introduce you to diatropic rearrangements. Then we will see some new applications of photochemistry. Okay. Not in detail, some new application which is right now happening in the field. Okay. So first we will get into this diatropic rearrangements. Okay. So what is diatropic rearrangement is all about? See, pericyclic reaction which involves involve concerted intramolecular migration of two sigma bonds. Very important. See, it should be concerted, it should be intramolecular migration of two sigma bonds simultaneously. Okay, are known as diatropic rearrangements. So the word is that it should be concerted process. Okay, it should be intramolecular migration. It should be an intramolecular migration. Important is two sigma bonds, and they should happen in simultaneously. Okay, so concerted process, intramolecular migration of two sigma bonds happening simultaneously. This type of pericyclic reactions are called as diatropic rearrangements. Basically, in diatropic rearrangements, there are two types. Okay, again, they can be classified as two types. Type 1. In type 1, two migrating groups interchange their relative position. That is in one case. In type 1, you can see, I will just shut it off. Diatropic rearrangements fine. They can be again classified in two. They can be called as type 1 and type 2. Type 1 and type 2. So type 1 is, in type 1 what happens? It is two migrating groups interchange their relative position. Okay. Two migrating groups interchange their relative position. They fall under type 1 of your diatropic rearrangements. In case of type 2, it is your bond, okay, not the group. In this case, it is your group. In this case, the sigma bond are migrated to new bonding site. But important is that without any positional interchange. That is very important. Any positional interchange for groups. See, So, first what I said, what I defined for diatropic rearrangement. Diatropic rearrangement should be a concerted intramolecular migration of two sigma bonds simultaneously. Okay, then you that type of pericyclic reactions you call them as diatropic rearrangements. In diatropic rearrangements, it is basically classified into two types, like type 1 and type 2. In type 2, it is an interchange between two migrating groups, that is basically interchange of two groups, okay, which are involved in the migration. In type 2, it is nothing but its sigma bond moving to the new bonding site, but important, there should not be any positional interchange of groups. There should be no positional interchange of the groups. So, what we will do, we will first see type 1 and then we will see the type 2. So, type 1, we will take a simple example of type 1. See, you have an alkene, okay, I call this as R and R1, okay. I do a reaction on this. So, what happens, this is my two migrating groups, these are my migrating groups. This two what type 1 definition says, the two migrating group should interchange each other, clear. These two migrating groups will interchange each other. So, basically I get a product like R1 and R. So, you get a interchange of two groups to give you this product. So, basically how to I have to understand this, how this happens. For example, if I take the same molecule R to R1, so just thinking about the transition state, how it can happen. So, I can have a transition state like this with my R here, then my R1. Like this, I can think of a transition state. Clear? And this then can get me change in my R to R. So, this is your type 1 mechanism, type 1, okay, type 1 diatropic rearrangement. So, type of concerted, and you can see two groups, they interchange their relative position, they just interchange their relative position, clear. So, you see an example, very nice example. We can take a molecule, you can have an R1 here, okay, R2 fine, I have this one. I have my, see the stereochemistry, I have a bromine here, okay, the same bromine I am going to have again. Now, if you take this, okay, and do the reaction, I get this product, very interesting, same product. This is my R1, okay, which is going to tell my, now if you see my bromine, they are completely interchanged. See, to fix that, whether this two bromine, I have kept this R1 and R2, and you see the stereochemistry of this. This bromine has been completely interchanged. Okay, how this can, same way as we write, we can write here also. You know, R1 here, R2. Then bromine here, you get a transition type of state where I can write like this. Two, but like this type of way, BR, BR. So now they can easily interchange to give my product. R1, R2. Then you have your BR and my PR. See, this you call as a type 1 diatropic rearrangement. Any doubt with this? So, this is called as type 1. Okay. Now, we will see the type 2, how it works in type 2. What type 2 defines you? What it defines? It says that the sigma bond are migrated to new bonding site, right? New bonding site, but without any positional interchange, without any positional. Why I am writing this definition? Because it will be helpful once we see the example. Interchange for groups. Now we will see the example and see whether that fits with our definition. So I take then with this molecule, okay. I have a double bond here, fine. In this case, I keep my hydrogen, but one way I keep my deuterium and I keep my deuterium here. Okay. Instead of hydrogen, I made it a deuterium. Now, if you see this reaction, you get a product. See the product will be not the interchange of the group, but the product will be more like an interchange of the sigma bond, okay, with my deuterium hydrogen. There is no potential interchange, okay, give my this one. See, so this is the type 2. How it happens? Just to understand what the transition state can be. Okay, you have now. So what happens? You have a hydrogen here, right? Hydrogen here. You have a deuterium here. Deuterium. This double bond you have here. So this deuterium just moves across this. Fine. This can be the transition state. This is your deuterium. It just moves across here. Okay, they just bend to deuteriums moves here this direction to give you the product. Clear? So this is your type 2 of your diatropic rearrangement. So these are the two types of your diatropic rearrangements. So just I want to just brief you out what is diatropic rearrangement. And diatropic rearrangement is a class of your pericyclic reactions in which two sigma bonds undergoes a rearrangements intramolecularly the concerted, and the movement of your 2 sigma bonds should be simultaneously. And then there are 2 types of diatropic you can think about. One is type 1, another is type 2. In type 1 there is a migrating group interchanges. In type 2 it is the sigma bond moving to the new bonding site, but without any positional interchange of the group. Clear? So, this is your diatropic. So, if you that is more about your end of your pericyclic reaction. So, if you see what we have studied in pericyclic reactions. So, what we have studied in pericyclic reaction. So, initially we first talked about your important reaction, that is your sigmatropic reaction, right. We studied about sigmatropic reactions, studied this class sigmatropic reaction. In sigmatropic reactions we studied about different type of sigmatropic reactions, like we have studied hydrogen group moving, then bonds. We have studied like in group moving we have studied hydrogen atom, methyls and like that, and then we have studied about the sigma bonds movement, where we have studied your cope, oxycope, Claisen, and we have studied different type of Claisen rearrangements, and we have yes, and we have studied, and there we have understood their stereochemistry also in detail about sigmatropic reaction. After finishing sigmatropic reactions, then we studied another important type of pericyclic reaction, that is your cycloaddition. So, we have studied cycloaddition reactions. We did lot of cycloaddition reactions. We have in that we are concentrated more on our Diels-Alder reactions. We have studied 2 plus 2 cycloaddition, 4 plus 2 cycloadditions. We went even 4 plus 4, and we have dealt many about their stereochemistries and all about. Okay, we finished sigmatropic, then we studied cycloaddition reaction, then we went for Ene reactions. Ene reaction is nothing but it is a group transfer reaction, right. Then we studied group transfer reaction. We studied group transfer reaction, nothing but it is a Ene reaction, in which we understood the Ene reaction in detail, how the Ene reaction works and all these things. After studying this group transfer reaction, then we moved to electrocyclic reaction. We studied electrocyclic reaction. So, these are the 4 important electrocyclic reaction. What we in electrocyclic reactions we studied their cycloaddition, opening, ring opening and ring closure, Korn, Dis, and their stereochemistry, how they open the mode and all these things. So, these are the 4 important class of reactions we touched: sigmatropic, cycloaddition, electrocyclic reaction, group transfer reaction. Then, like previous class, we also discussed one more important class, that is your heliotropic reactions. So, we studied the heliotropic reactions in detail. After studying heliotropic reaction, today we have just even outlined little bit about your diatropic. Today what we studied? We studied diatropic rearrangements. Okay. So, this what we have so far studied on the head of pericyclic reaction. We have studied sigmatropic, cycloaddition, group transfer reaction, electrocyclic reaction, heliotropic reaction, and diatropic reaction. So, we have the most of this are the important major class of your pericyclic reactions, which we have studied in detail. So, that sense about our pericyclic reactions. Now, what I am going to do, since we have discussed about our photochemistry in the first, like in first 20 or 24, 23 lectures, we have discussed about the photochemistry, where we have studied all the natures about your carbonyl chemistry and all these things. And then after later off, we have discussed on our pericyclic reactions. We have finished pericyclic reaction. Now, as a last thing, since the last class and the last thing, what I want to do is that I want to just introduce you to some new field in the application of photochemistry, because that's our growing up in the new areas. One of the important applications. So, we will concentrate the remaining the next few minutes, for next half an hour, we will try to concentrate on the applications of photochemistry. Okay. See, one of the hot field nowadays is controlled release, or you can call it as controlled delivery, okay, of drug molecules, or even you can call them active molecules. Okay, controlled release or controlled delivery of drug molecules. This has become a really an important field, and there are many ways you can release drugs in a controlled fashion. Okay, the one of the best the way people do is that based on your pH. So, you know your system as different. Once you have a system, okay, you take your drug molecule, you coat it up with some polymer, and that polymer, once it goes to your pH, if it goes to acidic pH, then that polymer breaks down and the drugs gets released. So, that people are doing that pH controlled delivery of your active molecules. Then even by heat you can break the molecules, then you can deliver them. So, there are many methods like that. Now, like for last few years, using light as an external stimuli has become very interesting in the controlled delivery of active molecules. So, release, controlled release using external stimuli like light has become really interesting nowadays. So, why it is so interesting? What advantages provides than your other methods? Why it has become so interesting about light? See, this use of external stimuli, like you are using as an external stimuli. Okay, for example, you are taken a drug, okay, inside your body, and you have some peripheral cancer on your skin, and by using external light, okay, if I shine light or laser, whatever it is, and then if I can release that part alone, okay, then it will be interesting. So, that your other part, it's not, other cells are not damaged, only the cancer cells are damaged, right. So, that becomes, so the basic advantage this provides, this method, is that spatio-temporal control over the release. This is what your light gives, which is spatio-temporal control over the release. This advantage you get when you use light as an external. What is the spatio-temporal? Basically, what it says that at any space, given space, you can release. I can shine in this space and get it released, and or in the system like that. Temporal is that you have a gray. So, for example, I can switch on my light, switch off, because it is an external stimuli. For example, if it is pH like system, you cannot switch on or switch off the system. But if you are using a light as an external, okay, once the drug is released for 10% or 20%, then you switch off the light, and later if you want, you can switch on. So, you have a control, like temporal control over the release rate. So, that's the biggest advantage you get using external stimuli. That is why people are now working using external stimuli light for controlled release of drug molecules. So, how they do that? Basically, for example, you take an active molecule. Active molecule in one sense, I am for example, I am going to deliver anti-cancer drug. Okay, delivery of anti-cancer drug. So, that anti-cancer drug is my active molecule. So, there are many anti-cancer drugs are available in the market, right, which have activity, basically chlorambucil, camphothecin, like, okay. So, this will be my active molecule. So, that is my anti-cancer drug. Now, what I do is that I will take another molecule which we call as photo removal protecting group. What? Photo removal protecting group. What is this photo removal photo removable protecting group? This we call as PRPG. What is this photo removal protecting group? What it means? Basically, we know about protecting groups, right? So, what you do, you have a functional group, you have 2-3 functional groups. So, you want to protect one functional group and then carry out some reaction on other functional group, and later on you do a acid or base cleavage and remove this functional group to retain the functionality of the molecule, right. So, what a photo removal protecting group is used is that same way you attach this molecule, instead of using an acid or base to remove the protecting group out, you use light, that is all. Okay. Instead of using acid or base, you can use light to remove your protecting group. Then you call them as photo removal protecting groups. N number of photo removal protecting groups, because of that N number of photo removal protecting groups are used, because if your molecules are highly sensitive to acid or base, the other side of the function groups, then you cannot use it, right. In that case, you can use photo removal protecting group, because once you shine light, it is not going to affect the other part of the molecule and you can cleave them. So, it has been used in lot of organic synthesis, and many photo removal protecting groups are synthesized. You can have an like orthonitro benzyl protecting group, orthonitro. This is very commonly used, benzyl. Orthonitro. You can have, then you can have your active molecule here. You can have orthonitro-benzyl chromophores, they are very much used. Then para-hydroxyphenyl compounds are used. You can use para-hydroxyphenyl. People have used even. You can use coumarin. You can use even coumarin. And there are many others, like you can use benzoin. Benzoin is well known. Quinolines. So there are many photo removal protecting groups have been designed. So you have some are good for releasing acids, some are good for releasing phosphates, calcium, some can release in a longer wavelength like 410. So depending upon your reaction condition, your need, you can select the photo removal protecting groups. Okay. So these are photo removal protecting groups. So you take that photo removal protecting group, okay, just you have to shine light, then the photo removal protecting group comes out, releasing the molecule. So what you do is that you take the active molecule. For example, I am taking active molecule like chlorambucil, which is my cancer drug, anti-cancer drug, and then I take my photo removal protecting group. You can take your photo removal protecting group like coumarin, so that it can be water soluble, or it can absorb at a longer wavelength, so that your cell is not affected. So there are protecting groups which can even absorb at 410 nanometers. So you can select that type of photo removal protecting groups, and the protecting groups which it should not be after it releases, it should not be toxic to your system also. So keeping all that point into consideration, you can select your photo removal protecting groups, and several photo removal protecting groups are even be designed nowadays. So now what you do is that you add them covalently. Okay, most of the case you add them as a covalent, you attach them covalently, and you call them, basically in photochemistry they call as caged molecules. Okay, take the active drug, you attach it to a photo removal protecting group, then you call them as a caged molecule. Clear? So the important point of this caged molecule is that the activity of this drug, okay, will be get lost. That is, basically this molecule will be inactive. You should attach your protecting group in such a way that, for example, if that OH of your molecule is the necessary for its activity, then you attach your photo removal protecting group to that OH, so that the caged molecule becomes inactive. Now, after this, then you shine the light externally. So you see, depending upon the protecting group, you can find out your wavelength. It can moves from 310 to, you can even for 410. Nowadays people have used 700, that is based on your 2 photon absorptions are there, right. Same molecule, for example coumarin, which has an absorption at 350, then 2 photons it can do at 700. Coumarins are known to do 2 photon absorption, quinolines, and this type of molecules are shown to do 2 photon absorption. That means you can use 700 nanometer. 700 nanometer you can use laser. So you are not going to kill you are not going to damage the normal cells. So that becomes much more safer if you go for 2 photon approach. See, you cannot use 310. See, if it is a system for example, your active molecule is like a agrochemistry, then it is fine, you are not worried about the wavelength. But if it is active compound like anti-cancer drug, you want to take it for your body, then you are worried about your wavelength, right. 310 is not safe, because that itself will create cancer. So it's always safer to go above 400 nanometer, and it is much more safer when you go to 700, and that can be done by your 2 photon absorption method, like coumarin does. The same coumarin protecting group absorbs at 350, same way in 2 photon the same group absorbs at 700 nanometer. Clear? So you can shine light of that wavelength, and then you can release your active molecules. Once you do this type of release, you can, as I said, you can have a spatial control. This part you want to release, because you can other part you can close by your black cloth and just shine light on this part. So you have a control over that, because it's an external stimuli. Then temporal control, whenever you want it, you just switch on the light. Whenever you don't want, you switch off the light. So that great advantage you get by this method. Based on this method, now this method has been control delivery of anti-cancer drug using this type of methods have become like eventually now new field, and many good papers are coming out of it. So the recent development, if you see on this type of work, that is delivery of anti-cancer drug by using photo removal protecting group, is becomes like different. Like now it has went one step ahead, and people are calling them as photoresponsive nano carriers. See, same system, okay, photo removal protecting group. Slowly now people have changed little bit and made it as a photoresponsive nano carriers. What is that? Again, this is going again, it's a photo removal protecting group, but your photoremoval protecting group is not now attached to a nanoparticles. So, what advantage is going to give you now? See, for example, like people are using mesoporous silica. You can use nanoparticle, like people are using mesoporous silica. This is your nanoparticle. Then people are even using gold, and you have several nanoparticles like that you can use. Now you take your nanoparticle, basically you functionalize your nanoparticle, like in the end you try to have some groups like OH or whatever you want, you functionalize this. So, you have a nanoparticle, so you will have a functionalized nanoparticle now. You have a functionalized nanoparticle. So, why I am saying this, see, so far you have seen the basic of photochemistry, but you should know the real field, real what is happening right now in the photochemistry field, because that is very important for you. So, you have a mesoporous silica, they are taken a nanoparticle. What are they doing? Just functionalize this nanoparticle. Now, interesting part, what they are doing. What we did initially, we just took our photoremoval protecting group and attached to our anti-cancer drug. But here what they are doing, they are taking this photoremoval protecting group, then they are attaching to your nanoparticle. Now, what happens? You will have a nanoparticle, with the end you will have a photoremoval protecting group. So, you will have a system like this now. Like this you can construct if you want. Once you construct like this system, now what happens? This is called as photoresponsive nanocarrier. See, you know there are several advantages when your delivery system becomes nano, because its half-life time is increased, its toxicity becomes less, and its getting into the cell permeability becomes more, right. So, you have n number of advantages. Once a system, once your delivery device becomes a nano shape, then you have a lot of advantages, like the best advantage, toxicity becomes less, permeability becomes more. You can do for different oral administrations, right. Now, what they do, once you attach this photoremoval protecting group, now you can attach your anti-cancer drug as in the previous case, right. Now, you have a nanoparticle, where you have a photoremoval protecting group plus anti-cancer drug. Like this you have a system, like this you will have photoremoval protecting group and anti-cancer drug. So, like that you will have a nanoparticle. Now, if you shine light on this, now it is going, now what happens? This will have whole system will be nice, gets into the cell. Now, you shine light on this and you can see your anti-cancer drug is released in a controlled fashion. So, that is a new area slowly coming up. Not only on like nanoparticles, people have even used photoresponsive polymers. This is photoresponsive nanocarriers. People have even made photoresponsive polymers. You can have photoresponsive polymers, because that is again instead of nanoparticle, except you will have a polymer. So, basically they make a polymer. This polymer inbuilt will have a photoremoval protecting group. So, you construct a polymer which has a photoremoval protecting group. They will have photoremoval protecting group inbuilt inside. Now, this whole polymer, this you can make it smaller. You can make vesicles and micelles. Okay, it becomes very small, and then you can take your anti-cancer drug and you can load on them. But this will be more like a physical encapsulation. Your anti-cancer drug will be inside. It's made of photoremoval protecting group. That's all. That's what I want to say. Now what will happen? Now if I shine the light, okay, since we know that photoremoval protecting groups absorbs light, so it will cleave off. This will disrupt, giving out my anti-cancer drug. So like that people have made using polymer also. So first initially, so controlled delivery of active molecules are very important. Okay. So in first case what they did is that just they took your photoremoval protecting group, attached to your anti-cancer drug, they have shown that it can release, and they have found two good advantages, like it can have a great control over the spatio and temporal. These are the two given. After that what they did, they took the photoremoval protecting group, attached to your nanoparticle, so that it becomes a nano carrier. Okay. And then you attach your anti-cancer drug. Okay, then it become like photoresponsive nanocarriers. People in the place of nanoparticle, people are using mesoporous silica, like gold nanoparticles. So many of the nanoparticles are used nowadays. And then these are all about chemical encapsulation, like covalently they are encapsulated. But if you want to do a physical type of encapsulation, you can take a polymer, you build up a polymer which contains photoremoval protecting group. Okay. Then what happens, once you have this, then you make a physical encapsulation of your anti-cancer drug, then shine light, you know that your photoremoval protecting group will absorb the light, and then it cleaves off, giving you anti-cancer drug. So this is the hot field on controlled release of drug delivery. Okay. So it's not about only anti-cancer drug, just I'm taken an example. You can use it for any active molecules. See, the same photoremoval protecting groups have been used for release of calcium ions. Okay. Which is very important, because to study some biological process like ion channels. Okay, that's where they have been used for controlled release. People have used photoremoval protecting groups for release of ATP, ADP. Okay, to understand what happens in the biological systems. Okay, people have used to release neurotransmitters, to understand what process is happening in the psychiatric neuro diseases. So if you want to have, it's not only about anti-cancer, you want to have any controlled release, you can use photoremoval protecting group. You have to tie it up with the active molecule. Okay, and slowly sense them. See, now if your, for example, if your photoremoval protecting group is fluorescent, okay, then it will be much more useful. For example, amino acids, it's very hard for amino acids to calculate and all these things, because they are non-fluorescent molecules. So if you connect amino acids with your photoremoval protecting group, then you can now understand how the amino acid gets into the cell, how it interacts with the system by using your fluorescent instruments and all these things. Okay. So it's opened up a very good area, and several research is going on in this type of area, controlled delivery of molecules using your photoremoval protecting groups. Another area which I want to highlight is second area which we will discuss is about photolithography. You know about photolithography. I know that you have heard about photolithography, and it was just like a stamping process, right? Normally what happened is that you take a solid support, okay, it can be silica or gold, whatever, silica, and then you take a thiol, gold, okay, you take a thiol, then you keep a mask on this and shine light. Wherever the light goes, okay, shine light. Wherever the light goes, that area will be that you will have gaps. You can have like this, okay. This area, wherever the light goes, this will go off, and you can create a stamping. That's process that you have studied as a photoresist. But now what happened is that now it become much more interesting. People have started working on functional group photolithography. Using this, you can bring up the functional group. Basically, you create surfaces which can be hybrid surfaces like hydrophobic and hydrophilic. That type of surfaces you can build. How to make them is nice. Same photoremoval protecting group, using that. See, for example, you take a thiol, take a thiol and okay, you have a thiol like this. Take your photoremoval protecting group. For example, I am taking a photoremoval protecting group of orthonitrobenzyl with a fluorine chain in it. That means it is more hydrophobic. So, I will be basically protecting this by my photoremoval protecting group. It gets protected. Okay. Now, you take your gold slide. Okay, you can take a gold slide. Now, dip this gold slide into your thiol. You know that once you take your gold slide and dip it to your thiol, thiol has a great affinity towards gold. Okay, what it forms? You have studied that. Yeah, it forms a self-assembled monolayer. Okay, so you have a gold. Once you have a gold slide, it forms a nice monolayers. I have a sulfur here, photoremoval protecting group. It should be nicely packed. Okay, I'm just, since I don't have space, it will be nicely packed one. This is all your photoremoval protecting group, and it will be spaced. There will be not. It will be, all surfaces will be like this. They will be highly packed one. You get a surface like this. Okay. Now what you do? See, you can get mask. Okay, the mask of chromium mask you can get. Okay, you can have or you can make mask by yourself. Like you can have a holes like this in the mask. Okay, or you can have a mask of parallel like this. So you can get mask of type what you want. Okay, then you keep this mask in the top of your SAM, the new freshly prepared SAM. See, basically you have taken a thiol, you protected the thiol, then you made a SAM on gold slide, right. Once you made the SAM on gold slide, what you did, you kept a mask. Once you kept the mask, now what you do, you just shine light, like your lithography, just like your lithography. So what happens? The area where there is a hole, pinholes, okay, the light gets into that area. Other area it is completely masked. So then what happens? Once the area where the light gets in, your photoremoval protecting group, once the light gets in, what happens to your photoremoval protecting group? The photoremoval protecting group cleaves off to give you the functional group back. What was your functional group? OH, right? So wherever there was a light, so then you will have a SAM See, they will be always tilted like this, Sam. Okay, I am drawing straight, but they all will be tilted down. Okay, now wherever the light has not fallen, you will have a photo removal protecting group just like this. Okay, wherever the light has fallen, you will have your OH, because photo removal protecting group goes off. Then you have a OH. See, I earlier said that I have made my photo removal protecting group in such a way that I have a fluorine chain, right? Now my photo removal protecting group has a fluorine chain. So what it is? So basically it will be hydrophobic, and this will be hydrophilic. Now I have a gold surface, okay? A surface is hybrid. So this is hydrophobic. So I have a hydrophobic surface here, and this surface is hydrophilic. So I can create now hybrid surfaces using my lithography, function group lithography. So once you have a functional group, then you can play around it with, you can attach your lipid molecules, you can attach DNA, or you can do whatever you want on the hydrophilic sides, and you will have a bilayer system, and n number of applications are coming out of it. Okay. So this are now started new areas on thing. Other areas, you know that another new area which has been started is visible light photochemistry, for visible light photochemistry, you can say, using just visible light. Okay, just your ordinary light, people have started doing chemistry, that is using your ruthenium complexes. Okay, so you can use your ruthenium complex. Ruthenium complex absorbs light using your ordinary CFL bulb. Okay, and you can carry out all most of your reaction, like some important reactions have been carried out in the you doesn't need a big photochemical apparatus. You can just do the reactions in visible light itself using your ruthenium complexes. So that is also getting up. In environment, if you see, normally photopentons is, people are working on photopentons. That is also now it has become on the visible light area. What they do is that you can make titanium nanoparticles, okay, then you shine light, and then use that, so in titanium, then use that process to generate OH radical, and you can degrade pollutants. Okay, so that is also another area coming out. And the final nice area is photoresponsive surfaces you can create. This is also another good area which is people are working on, photoresponsive surfaces, where once you shine light it will be hydrophobic, after you shine light the surface become hydrophilic. That is another nice area coming out. And finally, now another area which people are working on is photoresponsive polymers, okay, for converting light to mechanical work. That's also new area which has been started on. So these are all like upcoming areas in photochemistry. Fine. So these are some of the applications of photochemistries, and there are many other applications which you know, photodynamic therapies and other things, but I have just touched on the new areas. Okay. So with this we will end our photochemistry and pericyclic course, and that's all, and best of luck for you. Thanks.